All right, so here we go into the delete. Now, I try to not make it sound too scary. It's really not once you follow the simple procedures, but I just want to make sure that it is clear. So what we're going to do is we're going to think of this tree structure while we're trying to make some deletes here, because there's three scenarios that could possibly happen when we're trying to delete a node. And that all depends on the number of children the node has that we're trying to delete. So I've copied over the tree structure over on the left here. Of course, we have a root of 12, which has 3, 6, 8 is its left child, and 18 and 21 as the right children. And before I move into this, I want to spell something out. Looking at this tree structure, you should be able to think about what order that the nodes were added in just by looking at this. So since 12 is the root, you would know that the order that this data was added in would start with that 12. From there, it could have either been the 6 or the 18. We don't know. So there's more than one correct answer here. Let's say it was the 18. Okay? From there, it could have been the 21, or it could have been the 6 still. Let's say it was the 6. And then maybe we added the 21 from there, and then let's say we added the 3, and then the 8. This is perfectly valid. Because there are a number of scenarios, the key point here is that the root was definitely that first number, okay? But depending on other things, the things on the same level need to be added in certain orders, but can switch back and forth between the two. Just as the same as if I were to give you this, I would expect you to be able to draw the tree structure from this order of additions. Okay? Anyways, let's move on. That would be the type of question I would ask on a test, for example. Okay. Let's look at this. So as I said, there are three possible scenarios for deleting a node from a binary tree. And again, that depends on the number of children that you have. The easiest and most straightforward one is if you're trying to delete a leaf node, 3, 8, 21. Remember, a leaf node is anything with no children, 0 children. Well, that's just as simply as saying, hey, kill it. That's it. So if we're trying to delete, say, the node with cargo 8, all we would have to say is, well, go back to your parent and set the parent's right child to null. And that's it. The garbage collector will come around and collect that node and throw it away because there's no longer a reference to it. It's as simple as that. Now, this is where I talked to you about before about having that parent connection. So the process would be find the number you're trying to delete and then go back to its parent and set the correct corresponding child to null. The alternative is to say find the parent of the node you're trying to delete and then just delete that parent's child. It can go both scenarios. I actually prefer the method where we find the parent of the child, just because that system is going to be consistent throughout all of our deletes and everything like that. And it just keeps things a little bit cleaner. But if you find it easier to deal with the parent connection, then do that. That's okay. Not the end of the world. All right, so basically all we're doing is we're just going to set the corresponding left or right child of the parent to null. Nothing else to it. And of course, you have to reduce your count in your binary tree by 1. So 3, 8, and 21. Now the next one is if your node has exactly one child. Well, in this scenario, we only have one option there, and that's the 18 node, right? 18 has 21, 6 got 2, 12 has got 2, so 18 is the only one we're going to delete. Now you think, well, how am I going to delete this? Well, what does that actually mean, looking at this picture? It basically means we say we want to get rid of the 18. So that means that the right child of 12 can no longer be 18. It's got to kind of hop over and now point to the 21. So we just basically kill this thing inside and then hop over and connect to it. So the way that we do that is it's like a two-step process. The first thing you're going to do is you got to set up the connection to that 21. So you got to be at the parent. So assuming you're at the parent or at the child, let's say we're at the parent. So at the parent of delete node. Basically all you're going to do is you're going to say, okay, I want to set my right, in this case the right because it's bigger, the delete node is on the right hand side. I want to set my right value equal to my child's right value. So think of our commands, what we have set right. So you would have set right. Now we're doing this inside of the parent, right? And what do I want to set the right to? Well, I want to set the right to my right child. So how do I get the right child? Well, I use get right. But I don't want the right child. I want the child of the right child, the right child of the right child. So I'm going to say get right dot get right. Now let's break this down so it doesn't look like complete craziness. So remember, we work for inside for. Oops, I missed a bracket in there. Where's my eraser? Put that back on here. So it's actually going to be like this. Sorry. So we're going to get the right child of the one we're currently in, so that's be the 18, but we want the right child of that guy, so that's the 21. And so that means we're going to set, so this whole thing comes down to the 21 node. We're going to set right of 12 to 21. So that creates this jump. And then you can just kill the 18. Right? Okay. Actually, technically speaking, you actually have to kill the 18 first. So what you would do is you would take this and you would say node next, or I guess node, let's call it temp right, is going to be equal to this mess here. Then you would kill the right child, right? So you would say set right to actually no, you don't need, I lied. Let's back that up. I lied. You don't have to do that. Because what's going to happen here is, let's put that back the way it was. I apologize. Getting ahead of myself here. What's going to happen here is when we do this connection and we basically kill this, that means that that connection to 18 no longer exists. So there's no reference to 18 anymore. What that means is that the garbage collector is just going to come and collect it. We don't actually have to do anything. All we're going to do is just break that connection. I apologize for that confusion. My fault. So we're just going to set right to the 21 node. And that's all there is to it. Okay? Let me see if I can back this up far enough to my original drawing. Come on, undo. You can do it. How far can you go? How many do you store? We're going to find out. Is it infinite? I doubt it. If it is an undo, quick little pro tip here. Typically, undo operations will actually use things like linked lists or something that we're going to talk about later on, which is something called a stack. There we go. We're back to normal here. Oh, really? There we go. So, one node, just delete. 0 nodes, just delete. One node, skip the node to be deleted. And finally, the big one, which is the one more interesting, would be to delete a node that has 2 children. So imagine we want to delete the 6, or even bigger, the 12. How does that work? What does that actually mean? Well, there's a step-by-step process here. There's a multi-step process here. So before we had simple one-line operations. Here we would just set the child to null. Here we would just set the child to the child's child. That seems fairly straightforward. But in this case, we got to move things around. So imagine we want to delete 6 from the binary tree. What does that actually mean? Well, if we just delete the 6, we can't just get rid of it, because where does 12 point now? Does 12 point to the 3 or the 8? Does that even make sense anymore? Well, I don't know. Let's find out. So we want to delete 6 from the node. So the first thing we're going to do is we're going to choose a path from the node that we want to delete. So if I want to delete the 6, I'm trying to delete this guy right here, I'm going to choose a direction. I'm either going to choose the left or I'm going to choose the right. Choose one and be consistent in your operation. So if I'm going to choose the left, fine. Let's choose the left. What does that mean? So once I've chosen the direction I'm going to go on, what I'm going to do is, if I chose the left, I'm going to find the maximum node on that direction. Well, in this case, there's only one node, so it's actually the 3. If I chose the right, I'm going to find the minimum node on that direction. So it's always opposite of the data if you think about it, because normally our data gets bigger as we go to the right. So in this case, I want the smallest node on that right-hand side, the smallest of the bigger nodes. If I'm going left, I want the biggest of the smaller nodes. Okay? Oops, over here. So find that branch and try and find the maximum or the minimum. Okay. Now once we found that, now in this case over here, we see that our 3 is the biggest on the left-hand side. So what we're going to do is we're going to take the value of that cargo and we're going to temporarily store it in a temporary variable right here. Okay. So we're just going to maintain it for a minute. Now what we're going to do is we're going to delete that node that held that value. So we're going to delete 3. Okay, by setting the left child of 6 to null. Same way, we're just going to call the delete function that we've already created for a node with no children. Okay, and then finally, the last step is we're just going to copy the cargo from this temporary node into this other node. We are going to copy. All right, so it's very important that you realize that we're just copying the data. The node itself is actually still the same node. We're copying all the data. Now, in larger, more complex systems, you may want to go into a little bit more detail and actually start shifting pointers and stuff, but the basic necessity here is just copy the data. So step number 1 is choose a direction. Step number 2 is delete the maximum if you went left. And step number 3 is to copy. Okay? Now, I showed it here in many more steps, but that's really what it breaks down to. Okay. So then you do a happy dance because, holy crap, you did it. So what is this? After we've done this operation, the system should look like this. 12. The right side has not changed. 18. 21. Then on the left side, it no longer points to 6 now. It points to 3. And that goes to 8. And we see we have a non-balanced tree. Boo. But it is what it is. We had to delete a node. Okay. That's fine. Let's do a more complex scenario. Let's say we wanted to delete the 12. The actual root of the tree itself. What does that actually mean? How would we go about that? Well, let me show you. We follow the exact same rules. First thing I'm going to do is I'm going to say, all right, I want to delete the 12. And I'm going to choose a direction. Am I going to go left or right? I'm going to make it as complex as possible so we can see how it works. Is I'm going to go to the left, which means I need to find the maximum, the node with the maximum cargo on the left-hand side. Well, that means I'm going to go left, and then I'm going to keep going right as much as possible. In this case, it's going to be the 8. So I'm going to store that 8 in a temporary variable. Boop. I got my 8. Now I need to delete that 8. It's going to go away. It's gone. Now I need to copy the value of that 8 into the node I'm trying to delete. So that means that this becomes an 8 now. And we're done. So what would this actually look like? That means that our 8 is now the root. Our left child of our 8 is the 6. Our left child of our 3 is of our 6 is the 3. There is no longer a right child there. It's gone. And then on the right-hand side, we have 18 and 21. This is what happens when we delete that root. Things have to be reorganized, but you can see it still follows all the valid rules of our binary tree structure. Wait, yes, that's right. I thought I wrote an 8 there. And that's it for deleting. So the next videos are going to go into a few more interesting details, not in terms of manipulating, but now in terms of analyzing our binary tree structure.